Hello there friends, welcome. I am sure many of you are familiar with the Triac. This component is often used to control the speed of universal motors. We find these motors frequently in home appliances like vacuum cleaners, blenders, and power tools. But this question is, how does a Triac control the speed of these motors? This is a sample module that uses a BTA16 Triac or a similar model. With this circuit, we can adjust the motor's speed. In this video, we want to use an oscilloscope to practically examine how a Triac works and understand the concept of the firing angle. So, stay with me until the end of the video.
Okay, what is a universal motor? A universal motor is a type of series electric motor that can run on both alternating current and direct current. That's why it's called universal, or in other words, all-purpose. In this motor, the stator windings and the rotor windings are connected in series. In DC mode, direct current flows through the windings, creating a constant magnetic field that makes the rotor spin. In AC mode, even though the alternating current changes the direction of the magnetic field. Because the current direction changes in both windings, the stator and the rotor, at the same time, the direction of the produced torque always stays the same, and the motor continues to spin. The main difference is that a universal motor can work with both types of current, while AC induction motors only work with AC, and standard DC motors only work with DC. Also, universal motors use brushes to transfer current to the rotor, whereas common AC induction motors are brushless and work based on induction. Because of this ability to adjust speed with voltage, a Triac is often used to control the speed of universal motors in AC applications. Okay, first I will draw the speed control circuit for you and explain how it works. This is a common speed control circuit using a Triac. The mains voltage, or the AC input, enters the circuit here. The 100 ohm resistor and the 100 nanofarad capacitor form the snubber circuit. This circuit is used to protect the Triac against voltage spikes or sudden jumps in voltage and prevent it from turning on unintentionally, especially when controlling inductive loads like motors. Initially, because the Triac is off, the circuit is inactive and no current flows to the motor. The AC current flows through the 1 kΩ multi-turn potentiometer and the 500 kΩ potentiometer, starting to charge the capacitor. When the voltage across the capacitor reaches above 30 volts, which is the diac breakover voltage, the diac turns on and sends a current pulse to the Triac gate, turning it on or triggering it, as we say. Once the gate is activated, the Triac turns on and conducts the main current to the motor. The job of the 1 kΩ multi-turn put is to ensure that even if the 500 kΩ potentiometer is set to 0, excessive current is prevented from flowing into the capacitor and diac, granting a minimum resistance in the charging path. But the most important component in this circuit is the Triac. A Triac is a power semiconductor device that can conduct AC current in both directions, meaning in both the positive and negative half cycles. To control the speed of a universal motor, a method called phase angle control or firing angle control is used. In this method, by changing the time the Triac turns on in each AC half cycle, the amount of effective voltage reaching the motor is controlled. This change in effective voltage directly adjusts the motor's speed. The next important component is the diac. A diac is a two-terminal semi-inductor device that acts like a voltage-depending switch. A diac has a specific breakover voltage, usually around 30 to 35 volts. When the voltage across the diac reaches this value, the diac conducts and applies a pulse to the Triac gate. This pulse causes the Triac to turn on at the right moment, allowing current to flow to the motor. The capacitor gradually charges until the voltage across it reaches the diac breakover voltage. When the diac conducts, a pulse is applied to the Triac gate and the Triac turns on. By charging the potentiometer resistance, the capacitor charging speed changes, and consequently, the time it takes to reach the diac breakover voltage and the triac firing angle are adjusted. Okay, how exactly does the triac adjust the voltage? The triac doesn't directly reduce the voltage amplitude. Instead, it affects the effective output voltage by controlling how long it stays on during each AC half cycle. This process is known as phase angle control or firing angle control. To turn the triac on, we need a gate trigger pulse at its gate terminal. When this pulse is applied, the triac turns on, and current flows between its two main terminals, which are usually called MT1 and MT2, or sometimes A1 and A2. Now, why is a diac typically used to trigger the triac gate? As we said, the diac conducts at a specific breakover voltage, usually around 30 to 35 volts, and sends a current to the triac gate. When the voltage across the diac, and therefore the current through it, decreases after triggering the triac, the diac returns to its non-conducting or off state. Furthermore, the diac is a symmetrical component, meaning it behaves the same way in both directions, for both the positive and negative half cycles of the AC voltage. If we remove the diac and, for example, use only a resistor to trigger the gate, the triac might trigger asymmetrically during the positive and negative half cycles. This asymmetry can lead to poor motor performance and generate unwanted DC noise. But the topic we want to examine today on the oscilloscope in this very firing angle of the triac. I have prepared a simple circuit here. Because I want to use a lower voltage, for example 12 volts AC, for better safely, I have removed the diac, which needs a higher breakover voltage, from the circuit and will connect the output of the RC circuit directly to the triac gate. This is practical at low voltages. The part number of this triac is BTA136 or a similar model. I also use a 1 microfarad capacitor and a 100 kilo-ohm potentiometer. We said that to adjust voltage with a triac, a method called firing angle control is used. The mains voltage is AC, meaning both its value or amplitude and its direction change over time. The mains voltage, which is typically 220 volts effective or RMS, has a peak value of about 310 volts. To control the power delivered from this voltage to the load, which could be a motor or a lamp here, using a triac, we need to specify when during each half cycle the triac should turn on. The AC voltage starts from the 0 point, rises to the positive peak, returns to 0 again, then enters the negative half cycle, reaches the negative peak, and returns to 0 again, and this cycle repeats. The RC circuit, meaning the resistor and capacitor, along with the diac in the main circuit, must be able to follow this cycle and determine the appropriate time to turn on the triac. By adjusting the potentiometer, we shift the moment the triac turns on in each half cycle. For example, let's say we want the triac to turn on so that only the final part of each half cycle, the last 30%, is delivered to the load. This means the triac is off from the 0 crossing point up to a certain angle, and then it turns on. This must happen similarly in both the positive and negative half cycles. Therefore, only this final portion of the voltage, whether in the positive or negative half cycle, reaches the load, resulting in a lower effective voltage and less power being transferred. We call the portion of the half cycle where the triac is off the firing angle. Although sometimes the angle at which it turns on is also called the firing angle. Here we are referring to the angle of delay before turn on. If the triac turns on earlier, for example, near the beginning of the half cycle, the firing angle is small. A larger portion of the half cycle voltage passes through and consequently more power is delivered to the load. If the triac turns on later, for example, near the end of the half cycle, the firing angle is large. A smaller portion of the half cycle voltage passes through and less power is delivered to the load. So, by changing the firing angle, the effective voltage reaching the load changes. This causes the power consumed by the load, like the brightness of the lamp or the speed of the motor, to decrease or increase. Okay, now we want to test this circuit. As I mentioned, for safety, I'll use a lower voltage, for example 12 volt AC from a transformer. I've removed the diac and I'm using a 12 volt incandescent lamp so we can see the effect of power change as a change in brightness. Probe channel 1, usually yellow, is connected to the AC voltage input, meaning the 12 volt transformer output, so we can see the reference wave. We connect oscilloscope probe channel 2, usually blue, to the Triac gate to see the trigger pulse. Alternatively, we can connect this probe across the lamp to observe the output voltage. Here, the RC circuit, consisting of the 100 kΩ potentiometer and the 1 microfarad capacitor, is connected between the MT2 terminal and the Triac gate. The load is connected between MT2 and the other side of the AC source. I'll turn on the circuit. First, by turning the potentiometer, you can see the lamp brightness changing. Now, pay attention to the oscilloscope. Channel 1 signal is the AC input sine wave, although with a lower amplitude here. Channel 2 signal, depending on where the probe is connected, is either the gate voltage or the voltage across the lamp. The firing angle is usually defined as an angle in the range of 0 to 180 degrees for each half cycle, relative to its starting point. When I adjust the potentiometer so the lamp has the maximum brightness, you see that the output waveform looks almost identical to the input waveform. This means the firing angle is close to 0 degrees, and the Triac turns on almost at the beginning of each half cycle. When I turn the potentiometer to dim the lamp, you see that the initial part of each half cycle in the output wave is cut off, and the Triac turns on later. This is a larger firing angle, for example, close to 90 degrees or even more. At a 90-degree firing angle, the Triac activates in the middle of the half cycle, and only the second half of the half cycle is delivered to the load. And if we could bring the firing angle to 180 degrees, the Triac would activate at the very end of the half cycle, or basically not activate at all, and practically no voltage would be transferred to the load, and the lamp would be off. This initial part of the wave that is cut off represents the time the Triac was off, and this latter part of the wave is the portion where the Triac was on and voltage was delivered to the load. So, what did we learn from this experiment? We saw that by changing the resistance in the RC circuit, we can control the Triac turn-on time or the firing angle, and consequently adjust the effective voltage and power delivered to the load. Thank you very much for watching. If you found this video helpful, please give it a thumbs up and consider subscribing for more content like this. See you in the next video.